All right, Karina.
Everyone. Yeah, welcome back. So today we have Jiahao talking about indices of vector fields on singular spaces.
Okay, I have to first to say this. In this talk, I will not try to be super rigorous. I'll present hand-wavy proofs, showing pictures and illustrating ideas by pictures, and making slightly false mistake, but easier to understand. So that's what this talk is about. So I'm going to start with a review on Euler characteristic and vector fields on smooth spaces, and discuss a relation between the Euler characteristic and vector fields on smooth manifolds. The very well-known Poincaré and Hopf theorem. And then we're going to generalize it to singular spaces and see some implications of that generalization. For example, in the end of this talk, we will see why this is not a real algebraic variety, which is not very trivial, right? It's hard to say, how could I know if this is a real variety or not? But it's a very easy counting in the end of this talk. Okay, we start by a review of Euler characteristic. Now in this talk, I'll assume every space is triangulated in the sense that a space X is built from vertices, edges, triangles, tetrahedrons, and etc. For example, a tetrahedron itself is a triangulated space. It has vertices, edges, and triangle as faces, and a tetrahedron itself. And also you can combine these together to form spaces. And if I have a triangulated space, I can define the Euler characteristic of a triangulated space by counting the number of vertices and minus the number of edges and plus the number of faces and so on. So it's alternating sum of numbers of so-called this k dimensional analog of triangle. So we would call it k simplex. Okay. So 0 simplex is a point, 1 simplex is a short line, and the 2 simplex is a triangle, and so on and so forth. So we count the alternating sum of the numbers of k simplex. That's the Euler characteristic of the space. Now, for example, the Euler characteristic of finite many points is the number of the points. So it's nothing, if you have a discrete set, the Euler characteristic is nothing but counting the size of the set. So Euler characteristic really should be thought of as a higher dimensional analog of counting. And another example is the Euler characteristic of a triangle, of not field triangle, is the number of vertices, which is 3, minus the number of edges, which is 3. So it's 0. Okay. Immediately from the definition, we can see two properties of Euler characteristic that I'm going to use many, many times in this talk. One is the topological invariance. What I mean is the definition of Euler characteristic involves a particular triangulation of a space, right? But it turns out it does not depend on the triangulation. That is because the Euler characteristic is designed in such a way when you, for example, if you remove a vertex, then you have to correspondingly remove the edges that are attached to it and remove faces that has this vertex, that has this point as a vertex. So in the end, it doesn't change the alternating sum, right? As you, for example, if you remove this vertex here, then you remove one vertex, then correspondingly you have to remove 3 edges and also remove 2 faces. But we're doing alternating sum. So what you really do is you have to multiply this by -1. So when you count the Euler characteristic. So and then this end up in not changing the Euler characteristic of the space. So it does not depend on triangulation. And moreover, which I won't prove, it is not only a combinatorial invariant, namely it does not depend on the triangulation. It is moreover a homeomorphism invariant. And even further is a homotopy invariant, if you know what homotopy means. It means it does not change when you continuously deform the space to another. Another special property of Euler characteristic is so-called, I call additivity of Euler characteristic. It means if you try to calculate the Euler characteristic of the union of two triangulated spaces, that's going to be the Euler characteristic of A plus Euler characteristic B minus Euler characteristic of A intersect B. Well, that is the inclusion exclusion, because basically Euler characteristic is doing counting numbers of vertices, edges, and faces. And since those objects, when you're doing the counting, they satisfy inclusion exclusion property. And when you take alternating sum, this property is preserved. Okay. Using these two properties, we can now find Euler characteristic of more general spaces. For example, if I want to know the Euler characteristic of the one-dimensional circle, then I just need to put any triangulation I like on the circle, which I can realize it as a not field triangle. And we did this calculation. This is 0. Right? So the Euler characteristic of S1 is 0. How about two sphere? Well, we can realize it as a not field tetrahedron. So there are 4 vertices. How many edges? 1, 2, 3, 4, 5, 6 edges. And how many faces? 4 faces, right? So the Euler characteristic is 2. Okay, now challenge. What is the Euler characteristic of the figure 8? Okay. I'm expecting answer from audience. Okay, someone just -1, good. Okay. Well, you can easily put a triangulation, for example, like this, right? And you can count the number of vertices and edges. Okay, I realize this formula can be put in a very nice way. That chi of, I turn this 8 around and I move the 1 to the left-hand side and boom. But this is identity involving 0 and 1 and infinity. And if you write chi as E, okay, just fake E, Euler. So it involves 0 and 1 and E and put them into equality. So it's very nice. Okay, so that's about Euler characteristic and a very amazing identity involving Euler characteristic. So next we're going to talk about vector fields, and then we're going to talk about a relation between vector fields and Euler characteristic. So by vector fields, I mean, first of all, the space it lives on is at this moment I would be assumed to be a manifold. Namely, locally it looks like an open set in Euclidean space, and that's called local chart of the manifold. And chart and chart are patched together by smooth maps. So you can talk about smooth functions on manifolds, and you can talk about, as you can talk about tangent vectors on open set in Euclidean space, you can talk about tangent vectors at points on manifolds. Okay. So a manifold, n-dimensional manifold, and a vector field V on an m-dimensional manifold is an assignment of tangent vector at each point of the manifold. So this vector has to be tangent to the manifold at this point. And I require this tangent vector varies continuously from points to points. So that's what I mean by a manifold, or by a vector field on a manifold. And we say a point P is a singular point or a singularity of the vector field V if v vanishes at this point, namely the vector you assigned to this point is the 0 vector. And we denote that by p is in the set of singularities, which I denote by sing of v. Okay, here comes the most important notion. The index of the vector field at a singular point. So suppose P is isolated singularity. That means there's no nearby singularities. There's only one singular point, and nearby this vector field is non-singular. Namely, it's not the value of the vector is not 0. So then what I can do is take a very small sphere. For example, it is n-1 sphere of radius, say epsilon, around this point. Then since P is an isolated singularity, the vector field restricted on this small sphere is non-zero, right? Is non-zero. So then I can normalize this vector, use this map first to define a map. First of all, it is a vector in Rn, but in fact, since we normalize, we know it lives in this n-1 sphere sitting inside the Rn. So this is called a Gauss map of this vector field nearby this point. And I define the index of this vector field at this point P to be the wrapping number of this map. Okay, so what do I mean by wrapping number? This needs a little bit more explanation. Okay, let's see. In the case n equals 2, we get a map. We should get a map from S1 to S1, right? And I checked that everyone here should know the notion of covering and pi1 of S1, because it's covered in the top G1. So the wrapping number from S1 to S1 is precisely how many times you wrap a circle around the circle. Okay. So it's counted by an integer. You can wrap around 1 time, 2 times, twice, 3 times. And it also involves orientation. So you can wrap around in a reverse direction, then it becomes negative. Okay. For n greater or equal to 2, what you get is a map from Sm-1 to Sm-1. It's not much different. It's also, you should think of this as a higher dimensional analog of the wrapping of circles. It's also classified up to continuous deformation by integer. So you can talk about I wrap around an n-1 sphere around another n-1 sphere by n times. And also orientation has to be taken into consideration. Okay. And a special property, okay, of this, okay, just to give you a better feeling of this wrapping number. Okay. Suppose I have a map from Sk to Sk. Then what I can do is to suspend this map. Namely, I have this Sk, I have this Sk. I can think of Sk plus 1 is the suspension from Sk, just by putting a cone over Sk and putting another cone over Sk and glue them together along this Sk. It becomes Sk plus 1. And then there's an induced map correspondingly. Like if I map the orange point here to orange point here through this map, then correspondingly after suspension, there's an induced map, just mapping this orange line to this correspondingly map to this orange line. And I map this point here to this point here, this point here to this point here. So this produces a map from pi k of Sk, well, to pi k plus 1 of Sk plus 1, and which is an isomorphism. What this means is that the k plus 1 dimensional wrapping number can be thought of as up to continuous deformation can always be thought of as a suspension map from the lower dimensional case. So as long as you know how to wrap circle around another circle, then you can keep suspending this map to produce at least generators of this pi n-1 Sm-1. Okay. And for n equals 1, the map from S0 to S0 is plus or minus 1, because S0 is nothing but 2 points. So there are 2 maps, basically, the identity map and the flipping map. So I would denote by plus and minus 1. So the wrapping number at this in the case when n equals 1 can only be plus or minus 1, okay, by my definition. Okay, just to give you a better feeling, let's look at several examples. Okay, this is an example when n equals 2, okay, because I honestly don't know how to draw vector fields in three spaces. So now the first example, following definition, I take a small sphere around the singular point. Then we see this map is precisely the identity map from S1 to S1, okay, because this map maps to the north pole and start wrapping this by mapping to, it's like you start at this point, and then you have this vector, this precisely maps to this point, so you turn and come back. So it's the identity map. It wraps around 1 time. So the index of this vector field at the singularity is 1. Now, this one next to it is an example of a vector field of index 2 at the singular point here, okay, which I won't check. And okay, now a challenge. Okay, what is the index of this vector field? Well, let's see. Well, let's take a small, this is the singular point here. Let's take a small sphere around it. We want to see how many times it wraps around the circle, okay? Well, the vector field on the sphere looks like, well, it looks like this. This circle looks like this, right? So the map from this sphere to this, from this S1 to this S1 is, well, at this point, it maps to the North Pole, right? It maps to this vector. And then when you go around in this direction, we see that this point corresponds to this vector. So you should map to this point. So actually it goes in this direction and slowly turns. And when it hit this point, it corresponds to this point, map to this point, and turn. When this point, South Pole maps to South Pole, and go this direction, it turns, slowly turns back. So the index of this vector field is -1 because it wraps around the unit circle in the inverse direction once. So the index is -1. It turns out there is an easier way to see the index of this vector field if we use the following property. Okay. This is the key property, as I didn't realize this until I was preparing the talk. This is the key property that generates the whole talk, and so this is the very important. Okay. Suppose I have a vector field already built on Rn, or n-dimensional space. Then I can extend it to a vector field on higher dimensional space. Suppose you think of Rn as a linear subspace inside Rn plus m. And then there's a normal direction. Then you can extend this vector field normally in the sense that look at this black vector field on Rn, and then you slowly add this green vector field to the normal direction. Then it is extended to the Rn plus m, right? And it doesn't create singularity. The only singularity is the singularity of the vector field inside Rn. And the previous is an example of this, right? If you look at this vector field, it is in fact a vector field on R1 and normally extended to R2, just by slowly turn this vector field into the normal direction. For this kind of special vector field, okay, a natural question is, well, I can think of it as a vector field inside Rn, then count its index. But I can also think of this as a vector field on Rn plus m and count its index. Right? It turns out this I call normal extension of vector field doesn't change the index at a point. So no matter you counting this way or the extended way, it's the same number. Okay. And that's essentially because the following. Normal extension correspond to suspension. As we know, suspension of map doesn't go from lower dimensional sphere to higher dimensional sphere, does not change the wrapping number. So if we can prove this correspondence, then it proves that normal extension doesn't change the index by definition. Well, I'll illustrate this by, again, by the previous example. Okay. So, okay, by the previous example. So cheating of this is a map from in Rn, okay, and this is the intersection is a Sm minus 1, and they have a map already built. Then you normally extend it. It's nothing but adding normal vector to this. But you see, this is precise, or at any level, when you go up in the normal direction, it's precisely the same map up to continuous deformation, a little bit continuous deformation. So in this case, the map from S0 to S0 is flipping the 2 points. And when you go up to the normal direction, this is also flipping the 2 points. And when you finally go to the North Pole, it maps to the North Pole. So it's precisely the suspension of the map from S0. It's a suspension of map from S0 to S0 to S1 to S1. And as we know, the index, the wrapping number in the from S0 to S0, this is -1 by flipping the 2 points. And we just checked that this map also has index -1. Okay. This is the index -1. So this fits. Okay. Okay, before I move on, is there any question? Because this is the very important. Okay, then I'll assume no. Okay, now we state the theorem that reveals the relation between vector fields and the Euler characteristic. It is theorem of Poincaré and Hopf, or it's first proved by Poincaré on closed surfaces and generalized to higher dimensions by Hopf. And Poincaré is in the 19th century, and Hopf is probably in the early 20th century. Okay, the statement is: suppose M is a manifold with boundary, but boundary could possibly be vacuum. And suppose V is a vector field on the manifold with isolated singularities, and if the boundary is non-vacuum, I assume the vector field is point outwards the manifold along the boundary. Then the Euler characteristic of the manifold is the sum of the index of the vector field at all singular points, which I would denote by the total index of the vector field. So now suppose you have a manifold and you have a vector field, then if I want to know the Euler characteristic of the manifold, I don't have to put a triangulation and count number of vertices or edges or faces. I just need to look at the singular points of the vector field and look at the index of this vector field, just count how many, see how many times it wraps around, and then add them up, and then it becomes the Euler characteristic of the manifold. Okay. To prove this theorem, we must prove that, first of all, the total index of the vector field actually does not depend on the vector field you choose, right? Because the Euler characteristic does not depend on vector field. And then prove that, well, since it does not depend on a vector field, you can choose, you just need to find some particular vector field so that the index of the vector field is the Euler characteristic of the manifold, and finish the proof. Well, we will omit this part and leave this to the interested audience. And I'm going to show you how to construct an explicit vector field such that the total index of the vector field is the Euler characteristic of the manifold. We start by the case where the boundary of, there's no boundary, namely M is closed. In this case, we use a triangulation on M. Okay. We start by putting a vector field on the building blocks of M, namely put it on a triangulation or tetrahedra or higher dimensional analog case simplices. Okay, here's a vector field I use. We start from the vertices. Okay, I put a zero vector here. Okay, zero vector. Then I go to look at one simplex, which is the edges. What I'm going to put here is, well, I put a zero vector. I mark this. Put a zero vector at the center of this edges. And then from this zero to the other zero, I slowly grows this vector and then slowly decreases, or maybe use another color. Slowly increase this vector, increase the length of this vector and slowly decreases. So it is a continuous vector field along the edge from one singular point to another singular point. And similarly, I can do the same, and then decreases to zero. Okay. I do the same here. Bad join. Okay. So now I have put a vector field on one simplex. Then I have to extend it to two simplex. Okay. What I do is, again, I put a singular point at the center of this two simplex. And to the rest, well, I can do this. I normally extend this vector field a little bit from one simplex to the neighborhood of the simplex, to the one simplex. And then to the rest, it points towards this center and slowly reduces the length of the vector. And then if you have more simplex putting together, then you just do the same. And we can immediately see this defines a continuous vector field on the manifold. Let's count the index of this vector field. Okay. Well, where are the singular points of this vector field? Well, it has precisely one singular point at the center, or at the center of each K-simplex by my construction, right? I have a 0 at a 0 simplex, which itself is the center of itself, and have a 1 singularity at the center of edge, and 1 singularity at the center of the face, and similarly you can do this to higher dimensions. Then what is the index of this vector field at the on the center of the K-simplex? Well, since by my definition, what I do from K-simplex to a higher simplex is by normal extension. So to count the index of this vector field, I don't have to go to higher dimensions. I just need to count the index on this K-simplex. Well, but on this simplex, what is this vector field? On K-simplex, this vector field on this small sk plus 1 around the singular point is the antipodal map. Right? For example, here, you just point inwards. Okay, just map this point, map North Pole to the South Pole, map this point to the corresponding point here. So it's the antipodal map. So I just need to count the wrapping number of antipodal map from sk minus 1 to sk minus 1, which is, okay, as an exercising algebraic topology, this is -1 to the k. That's not very trivial, but that's the wrapping number of this map. Okay, so then it follows that the index of this vector field is, by definition, is the index at the singular point times the number of K-simplex. Oh, what is this? This is precisely the Euler characteristic of the space, by definition. Now that's the case where M has no boundary. Suppose M has a boundary, okay? For example, it looks like this. What I do is to cheat, okay? Cheat this part as M to the right of the screen, okay? And this is the boundary. And I attach a small piece in the middle to this manifold, this boundary of M cross 0 to a small epsilon, and I identify this as boundary of M cross times 0, and this boundary of M cross time epsilon. Then, as before, we have already built a vector field here, right? Like to the rest of here, and also we have a prescribed vector field pointing outwards of a manifold on this side of boundary. Then what I can do is to join these two vector fields by slowly, again, normally extend this vector field and turn this around to the normal direction and point outwards. And this becomes a continuous vector field on M such that the restriction to the boundary point outwards the manifold. And also despite that, and there's no singularity here. So it's the same counting as before. Then the number, then the index of this vector field is the Euler characteristic of the manifold. Okay, that's the Poincaré and Hopf theorem. As a corollary, we proved the very famous Harry-Ball theorem. That is, there exists no non-zero vector field on two-sphere. Well, that is because otherwise, suppose there is a non-zero vector field on the two-sphere, then since there's no singular point, the index of the vector field would be 0. So that means the Euler characteristic of the manifold must be 0, but that's not true. We counted this, the Euler characteristic of 2 sphere is 2, which is non-zero. A good picture of this is, let me show you the picture. Okay, is this, okay. Look at the Earth. Any vector field always has this singular point. You look at this swirling around cloud. You can think of it as a vector field given by the wind, and there's always one point where the velocity of the wind is 0. At least one point. Okay. Another corollary. Let's prove this. Well, how about, well, Poincaré and Hopf theorem says if a manifold has a boundary, then if the vector field restricted on a boundary point outwards the manifold, then the index of vector field counts the Euler characteristic of the manifold. What about a point inwards of manifold? As it turns out, the index of this vector field would count the Euler characteristic of M minus the Euler characteristic of the boundary. The proof goes like, okay, now suppose this is a V, right? And a vector field point inwards the boundary. This is M. What you can do is to make a copy of M and glue it along the boundary. So you make a copy. Now, I claim that I can extend this vector field here to the right, to the copy of M with only isolated singularities, which I won't prove. After extension, you would obtain a vector field on M together with M copy glued along the boundary. And if you go to calculate the index of the extended vector field by Poincaré and Hopf theorem, so the index of extended V should count the Euler characteristic of this, the whole manifold, the glued manifold, right? But by the additivity of the Euler characteristic, this should be the Euler characteristic of M plus the Euler characteristic of M copy, which is also M. So minus the Euler characteristic of the intersection, which is the boundary. Well, the index of vector field, the index of extended V is nothing but the index of V plus the index of V restricted to M copy, right? So on M, and this is on M. But now restricting to M copy, that's a vector field point outwards the boundary. And hence, by Poincaré and Hopf, this is the Euler characteristic of M. Okay, so if you cancel this with that, then this vector field has index being this. This corollary is going to be used as I'm going to discuss vector field on singular space. In just a second, okay. So that's Poincaré and Hopf theorem. It builds a relation between vector fields and Euler characteristic of the space. And the main point being, there's a main point is that a normal extension of a vector field does not change the index of the vector field. And as an important corollary of the Poincaré and Hopf is that if you have a vector field point inwards the boundary, then the index of that vector field is the Euler characteristic of the manifold minus the Euler characteristic of the boundary. Okay. Now we want to generalize this to singular spaces. Well, the motivation being, well, Euler characteristic can be defined for any space. And in some space, we can sort of talk about vector fields. And then we want to know if there's a relation between the vector field on singular spaces and the Euler characteristic of that space. And it turns out there is. But before that, we must make sense of vector fields on singular space, right? What do I mean by vector field on singular space? It does not have a tangent. It does not have a tangent bundle, right? Usually, like, because it's not smooth. And then we also have to make sense. What do I mean by index of vector fields on singular space? But on some singular space, a vector field makes sense. We can make sense of vector. We just need to make sense of tangent vector. But to make sense of tangent vector, we just need to make sense of tangency. There is a class of example of spaces which we can make sense. For example, look at, suppose you have an algebraic variety, which is the zero set of a polynomial or a bunch of polynomials. Then there is a large part where this space is smooth, called the regular part of the variety. So the regular part is a manifold. So on the regular part, you can talk about tangent vectors. Well, how about the singular part? Well, on the singular part itself is again an algebraic variety. So on the large part of the singular part, it is again a manifold with possibly a lower dimensional manifold. And then you can talk about tangency on that part. And then you can keep doing so. So we realize as long as a space has a partition into manifolds, then on each part, we can talk about tangent vectors. Then we can make sense of tangent vector and hence vector field. So this leads to our definition here. A stratification on a space X is a finite partition of X into manifolds. And then and each manifold in this partition is called a stratum of this space, and it's indexed by some set A. And we can put an order on the stratification on the stratum by if a stratum is in the closure of another stratum, we say this is a lower stratum, this is a higher stratum, and the lower higher is in the sort of in the sense that if S alpha is contained in the closure of S beta, it must be in lower dimensional than S beta, because as we'll see in the following examples. Okay. So the first example is suppose M is a manifold with boundary. Then it has a canonical partition, namely this part is a manifold of n dimension, and the boundary is a manifold of n-1 dimension. And the boundary of M is in the closure of the interior. And so boundary is a lower stratum and M is and the interior is a higher stratum. A pinch torus, we can stratify this space by points and the rest. And we can see that this point is in the closure of the two-dimensional piece. And also the figure 8, there's canonical point and the rest is a one-dimensional manifold. And this is an example of union of three planes in 3 space. And we can stratify space by, there is a bottom stratum given by this point and one stratum by this axis and the two-dimensional stratum by the rest. So, and as we see, this point is in the closure of higher stratum. So that's a stratified space. And now suppose X is stratified, we can make sense of vector field. It's again assignment of tangent vector at each point, in which varies continuously from points to points. And now we can define the index of vector field in a naive way. That is, we'll pick any point. Suppose that a point is a singular point. Then it must live in some stratum, which is a manifold. Then we can define the index of that vector field at this point by treating this as a index of a vector field on a manifold. Then we might think, oh, then, well, does the Poincaré-Hopf theorem naively extends? Namely, pick any vector field. We made sense of vector fields. Okay, pick any vector field with isolated singularity. Is it true that the total index of any vector field equals the Euler characteristic of the singular space. Turns out that's not true. So, for example, on this space, okay, I can put a vector field like this. Okay, there's a singular point here, and then it goes in like that. Okay, just goes in like that. Okay. So this is the only singularity of this vector field. Well, let's count the index of this vector field. Well, there's only one singularity. So we just need to calculate the index of this. Well, but this we treat as a zero-dimensional vector, a zero-dimensional manifold with 0 as its tangent vector. The index of this vector field is 1 by our definition. So the total index of this vector field is 1. But the Euler characteristic of this space is -1. So it does not count the Euler characteristic of the vector field. And as I just pointed out, the crucial point is that you cannot randomly put a vector field in the singular case, because it's sort of hidden in the definition. We define the index of the vector field by viewing it as a vector field on certain stratum. But, well, if I stratify the space in a different way, then I might get different index of the vector field. Or so it's proper to make the following definition, okay? If V is radial, we call V is a radial vector field. If near every point on certain stratum, it is a normal extension to higher stratum. This vector field here does not satisfy this property, because this point here, the vector field is not a normal extension to higher stratum. Right? The vector field near this point looks like this. But a normal extension should look like this. Right? Because you treat this as a one-dimensional manifold, and the normal extension of zero vector field should look like this. Right, here's an example of normal extension. I have zero vector here and normal extended, normal extended, normal extended, normal extended. So this is a radial vector field. And now this is a theorem of Marie-Hélène Schwartz. Assume X is it's stratified space and the stratification is good. It's called Whitney stratification. And V is a radial vector field on X. Then the index of a radial vector field counts the Euler characteristic of the space. So it's not true that any vector field counts the Euler characteristic, but radial vector field does. But before we go to discuss the proof of this theorem, let me tell you something about this Marie-Hélène Schwartz. So she's a very good female French mathematician who is known for her work on characteristic classes of singular spaces. And her family is also like a very strong mathematical family, sort of. Her husband is Laurent Schwartz. If you're working on complex geometry or complex analysis, you might have heard of Laurent Schwartz. And if you haven't heard of Laurent Schwartz, you must have heard a student of Laurent Schwartz called Alexander Grothendieck. And in fact, the father of Marie Schwartz is also a good mathematician. Paul Lévy is a probabilist. So good mathematicians in French, it seems like tend to union in families. Okay, let's go to discuss the proof of this theorem and draw some applications. I won't discuss in the full generality, but I'll show you in an example. Okay. Let's first build a vector field whose index is the Euler characteristic of the space. Now, also, again, I won't prove that the index of a radial vector field does not depend on a vector field. Okay. So what I do is to inductively build this vector field from bottom stratum. And once that's built, I normally extend to higher stratum to a neighborhood, and then go into the higher stratum, and then inductively build a vector field on higher stratum and keep going. So we start by bottom stratum. I put a vector field here, the zero vector in this case. And then I normally extend it to a higher stratum, okay, like this. So, and then I want to define a vector field to the rest of this one-dimensional stratum. But in this case, what do I see? Well, I already put a vector on here. What is the rest? Oh, I realized the rest is a one-dimensional manifold with boundary, with prescribed vector field point inwards this manifold. So I can do as before. I extend this vector field to the interior of this one-dimensional manifold with isolated singularities. Okay. So then I've extended to the one-dimensional stratum, and then I can keep going. I extend normally to a neighborhood of this lower stratum, and then again, I will see at a higher dimensional stratum, I see a manifold with boundary with prescribed value of the vector point inwards the interior of the higher stratum. So by induction, I put a radial vector field on this singular space. Now let's count the Euler characteristic, count the index of this vector field. Well, by induction, suppose we're on a lower stratum. Suppose by induction, the index of the vector field on certain lower stratum counts the Euler characteristic of the lower stratum. Then, okay. Then the vector field on higher stratum counts. So the index of the vector field on lower stratum. So the total index is the index on lower plus on higher, right? The lower, we assume by induction, counts the Euler characteristic of the lower stratum. On the higher, what do I see? Well, that's a manifold with boundary, and the vector field points inwards the interior of the higher stratum. So it's going to be the Euler characteristic of the higher stratum minus the Euler characteristic of the boundary of the higher stratum. Oh, but by additivity, that's precisely the Euler characteristic of the total space. Because the boundary of the higher stratum is the intersection of the higher stratum with the neighborhood of the lower stratum. So that proves that this vector field counts the Euler characteristic of the vector field. And essentially, that's the proof that any radial vector field counts the Euler characteristic of the space. Okay. As an application, we can prove a theorem of Sullivan. Is that suppose X is a variety over C, namely it's a zeros of a polynomial with complex coefficients, and over each point at each point in X, we can locally embed this variety into a affine space, which is a Cn. And the link of P in X is defined to be the intersection of X with a small sphere around this point. Then the theorem states that Euler characteristic of the link is 0 for any point. Okay, the proof goes like, well, use the vector field built by Marie-Hélène Schwartz. There is a radial vector field on here, on the radial vector field, so it points in the radial direction, sort of. And then we have a vector field on the link. Then okay, the next is a marvelous. I apply J to this vector field. The J is, you can think of it as a multiplication by square root of -1. On surfaces, is exactly turn this vector by 90 degrees. But what it does here is going to turn the normal vector into a tangent vector, okay, of the link. So it's a tangent vector field. On link. And the link has an induced stratification. And since this vector field V is radial, the induced turn, this J of V is radial, is a radial vector field on the link with respect to the induced stratification. So by Schwartz theorem, this vector field has no singularity. Then the Euler characteristic of the link must be 0. Okay. And as a corollary, we have a analog in real variety. So if you have a point in a real variety, you can also look at the link. The statement is the link of a point in real variety must be 0, have even Euler characteristic. And the point being, any real variety can be thought of as a fixed point of conjugation action on a complex variety. So the link of a point in the real variety is in fact the fixed point of a conjugation action on its complexification. So there's a involution, and this is the fixed point. So because of this involution, we see that this maps point, you can put a nice triangulation so that if there is a point, if there is a vertex here, then there's a vertex on there. And then, suppose this is a PXR. Then a triangulation would just pair up by this involution, and the fixed point must have an even characteristic, because the rest of the space has even characteristic and the total space has 0 characteristic. Okay, now we come to the example at the beginning of this talk. This space cannot be a real variety. That is essentially because you look at this point. Okay, what is the link of this point? That's the intersection of a sphere, right? That's this. Okay, now what is the Euler characteristic of the link? Well, that's 1, 2, 3. That's 3. Oh, what's 3? Is 3 an even number? No. So that cannot be a real variety. Okay, now the final quiz. Is this space a real variety? Which is 2 cones glued along a line. Is this a real variety?
I don't think so.
No, why? No, I mean, your answer is no, but why?
So we look at the figure 8, right, which is the link.
Right.
And the Euler characteristic is in fact -1.
Right. So, and -1 is not an even number, so it cannot be a real variety. So, okay, I'll stop here. Okay. Well, I'll stop here. Well, let me make a final remark. I want to make sure that everyone appreciates Marie-Hélène Schwartz's work on singular spaces. It turns out it has more applications than Sullivan's theorem. It can be used to study the singularity of an algebraic variety and to define characteristic clauses for singular varieties, and has many rich applications beyond this talk. And also a remark is that even though this theorem I stated here is due to Sullivan, it is first proved by Deligne during a conversation with Sullivan, but actually Sullivan's theorem applies to a more general space than complex algebraic varieties. And the proof I present here is due to neither Sullivan nor Deligne. It's in fact due to Borel. So, okay, that's all I want to say.
All right, Thank you, Jiahao, for the excellent talk. Are there any questions?
Oh, I just question, like, can you briefly explain what is the idea to define characteristic classes for singular varieties? I think you prepared like.
Yeah. So the main idea here is to use obstruction theory. So as we classically know that a Chern class for a vector bundle, or if it's a smooth manifold, complex manifold, you take the tangent bundle, that's a complex vector bundle. So it's the obstruction to finding framings. Right. But we realized by Schwartz's work that instead of using an arbitrary section of the tangent bundle, namely vector field, we have to use radial vector field to detect the correct invariant of the space. So correspondingly, if you try to make sense of the correct framing, then you have to use a notion of radial framing. So you look at the obstruction to construct radial framing on singular spaces, and then using obstruction theory, you would create the cycle, co-cycle, cohomology class, and hence the correspond. That's the correct notion, a correct way to define obstruction cycles and co-cycles. Yeah, that's essentially the point. You have to make sure everything is radial.
Is it? Oh, thank you. Yeah, for like, is it related to some like a Morse theoretic? Radial is like a unstable.
Yeah,
I consider unstable
I think so,
manifold.
but I don't know much about that. But I know people talk about this, like study this, like some Morse theoretical point of view, and you have to. Well, I think maybe McPherson probably has a developed a theory of a Morse theory on singular spaces, and I think it should correspond to a very similar discussion. And in fact, the Chern class for singular varieties is also defined by McPherson in the 80s. It was only in the 70s, and in the 80s, people realized that Schwartz's way of defining Chern class is identical with McPherson's way of defining Chern class. But anyway, that's another story. Maybe it's not a good answer to your question.
Oh, thank you. It's really great. And I think, no. I think it's yeah. Thank you for our great talk.
All right, thank you. So I think that's all the time we have for today. So yeah, see you all next week.
Okay.
Thanks very much, Jiahao. Very good talk.
Excellent.
I think the first time in a very long time I learned something about real varieties.
Yeah.
So yeah, that's good.
I'm glad.
Yeah.
It's understood.
It's like, you know, those algebraic geometers, they only talk about complex varieties all the time. So, you know,
yeah,
it's refreshing.
Yeah.
It is. Yeah.
Okay.
Okay. Thanks very much.
All right.
Take
Bye,
care.
everyone.
Yeah.